Okay, welcome everybody to our EOL seminar. I'm glad to see a bunch of well-known people here. And just try to add up the number of NCAR years assembled in the room. I think it's a lot. So it's very good. It's my pleasure to have a seminar speaker, a very distinguished seminar speaker, I understand now. Jothiram Vivekanandan. How was that? Good? Yeah, close enough. Okay. For that particular reason, he goes by Vivek. You all know Vivek, I guess, very well. You worked with him for many, many years. He is a senior scientist here at NCAR. The main body of Vivek's research is centered on his pioneering effort to characterize the microphysics of clouds and precipitation using advanced remote sensors. And he's actually among a small handful of researchers in the international community who mastered the theory, modeling, and observational aspect of atmospheric remote sensing. And I'm looking forward to hear a lot more about that today. For those of you who haven't been here at NCAR all that long and haven't participated in Vivek's career, he got his bachelor in engineering in 1979 at Madura Kamaraj University in Madurai, India. His master's in 1981 at the Indian Institute of Technology in Kharagpur. And I think right after that he came to Fort Collins, where he got his PhD in 1986. He joined NCAR in 1991. And has built his career here ever since. He did spend 4 years, and I guess there was always some travel to Kiruna, as a visiting scientist in the Swedish Institute of Space Physics in Kiruna, Sweden, northern Sweden. It's north of the Arctic Circle, so high up there. I hope you survived. It was cold there, I know. Vivek, he is a fellow of the AMS, and last year got the EGU Christian Huygens Medal for his pioneering and groundbreaking work on microphysical characterization of clouds and precipitation using advanced remote sensors. So with that, I'm done. Please let's welcome Vivek for his seminar titled Radar and Lidar Estimation of Liquid Droplet Size and Liquid Water Content in Stratocumulus Clouds. Vivek, please.
Thanks, Soger, for a nice introduction. Thanks to the HCR teams providing me the data sets necessary for this work. Also, Jon Jensen gave me profiles of Stratocumulus cloud droplets. It's very rare to have this kind of profiles of droplets in a cloud. And then Greg Memories from Rayleigh helped me with quite a bit of programming and other things with this. So with that, today, I mainly talk about Stratocumulus cloud. In NCAR, we do advanced measurements. We do produce a lot of products, like we have S-pole, we produce a particle ID, rainfall rates, using dual wavelength. We produce water vapor, MPD, dial. We do water vapor profiles. If we do all these scientific products, like K-band, S-band, we do produce water vapor and cloud liquid measurements. And when it comes to airborne measurements, using a LiDAR and radar, which is in G5, we don't have any products at this point. We do a very good measurements with the W-band radar, it's about 3 millimeter in wavelength, very sensitive radar. The LiDAR, which is a visible wavelength, gets a great measurements with attenuation corrected backscatter. But with all these things, we got a good measurements, we don't have any products yet. This basically seminar describes a possible product that will be implemented for stratocumulus clouds in a warm precipitation, no ice phase, it's just warm precipitation. Stratocumulus cloud, they're the most common cloud, like 23% of ocean, aerial coverage wise, 12% of the land. It's a very dominant cloud type. And these clouds basically are very shallow, 200 to 300 meter depth, and a lot of cloud liquid. Then the cloud liquid water content could be about 1/10 of gram per meter cube. And they're all very important to understand for radiation studies, for outgoing, incoming solar radiation, for cloud modeling studies, for CCSM. Then cloud depth could be more than 100 meters. When you find them, they may contain drizzle drops. That's a problem with that. In a lot of cloud droplets, the drizzle drops could be there. The presence of drizzle droplets makes it much more difficult to retrieving cloud liquid and droplet size. I'll show you why. This is a diagram showing a y-axis, the radar observations of D6 dBz. The x-axis, the liquid water content, a log scale. For a given dBz values, liquid water content could be anywhere in this curve, depending upon is it drizzle or is it cloud liquid. The reason being, the D6th, we got a 10 micron droplet, so 1 million of them. It's same as 100 micron droplet. The liquid water content wise, liquid water content 1 micron droplet will have about 1,000th of other 10 million 10 micron drops. That's the problem. It's both the same dBz values, but liquid water content much different just because the D6 and D cube relation between droplet size, liquid water content. And that is a problem what we face for having just radar observations. dBz alone is difficult to estimate liquid water content. We need additional measurements. Then what's the current status? Currently, we have power law relations like that. It all depends upon dBz values. Some of them use thresholds like less than minus 17 dBz assumes clouds without no drizzle. We have relationships like that. They're all based on in situ measurements with the power law, computing liquid water content and a D6th moment. Then you have clouds with the drizzle. There are relations like that. Basically, we have relations like minus 5 to minus 17 dBz, the power law relations like that, what you call Z, LWC relations like that, various coefficients, exponents you see it. And there are so many relations exist. For example, the studies done in 1950s, Atlas, even today, you can see based on dBz alone, so many relations exist, but they're so difficult to use them because they're so sensitive to droplet size. Again, the droplet size estimation, the effective radius, a power law or exponential relationship, what we see here. This is the latest one, in fact, 2012. That's what they're going to use it. And this is all based on a regression relation based on in situ probes. For example, a dBz or 10 dBz will produce about 40 micron droplet size. That's what it is. I give a general background on current status, the power relations what we saw. They were using a radar radiometer, having not only just radar alone, the radiometer, which is basically a passive instrument, which can give us a total liquid water pad. That could be used for getting a better estimate of droplet size liquid water content. And assuming, like dBz smaller values for a cloud and drizzle droplets like greater than 17 dBz, then we could estimate using a dual wavelength radars, the absorption, using a dial technique like having two different radars. Then if you could do that, then absorption, what you estimate, is equal to liquid water content, basically. You can do that. Because liquid water content and proportional to different absorption using a S and Ka band or two other wavelengths like that. But the problem with that is these two radars should have a matched beams. Otherwise, so difficult to do this because I have two different beam width, two different radars. It's not that easy to do this technique, but provided we have a good matched beams, we can do that. Provided there's not much mis-scattering, so many issues comes with that. In the radiometer liquid water path is basically used even other ways, like using a kind of a boundary, like you have a LWP estimate radiometer, then using a dBz, come with the LWC liquid water content could be done. And these are the techniques currently exist in the literature using radiometer and radar. Then about the radar and Lidar, there are techniques available in the literature, even with this. They use the reflectivity velocity, radial velocity, fall velocity of the droplet, spectrum width, for estimating basically particle size distributions. And that's done. Particle size distribution meaning it could be a gamma distribution, it could be a log normal distribution, right? You estimate those parameters. Then again, using a LiDAR observations, using an extinction, we can do the similar thing. But there is a problem. When you try to fit a distribution, the tail of the distribution may have a big drops that is not fully represented. That's what the problem is. We could estimate a log normal or modified gamma, but that's not good enough because you are going to miss the big drops which I showed you, which is a problem with remote sensing observations. And so we have to come up with a better technique. The current status, all of them assume a spectral size shape, either it's a log normal or a gamma or exponential, whatever. Then valid only over a small range of dBz values, like 0 to 17 dBz or less than minus 20 dBz, like that. Going to much larger dBz values, it doesn't apply anymore. You need to know the drizzle or it's a cloud droplets, otherwise you can't do that. And these are the limitations of current technique. So what we did, we tried to come up with a better way. To do that, we need to simulate the whole radar and LiDAR observations. For that, we have an NCAR hypercloud radar, which is the doubly band 3 millimeter wavelength. It measures up to 15 kilometer as in the L-band platform, the dBz and the radial velocity. Then we have a LiDAR, which is a visible wavelength, 0.53 micron or 53 nanometers. Again, that gives a attenuation corrected backscatter measurement, which is very important to have those kind of observation because the LiDAR measurements is not easy to correct unless you know that kind of observations. So one of them has about less than about 35 meter resolution, 37.5 resolution here, cloud radar. Here, range gate spacing. LiDAR about 7.5 resolution, like that. So we have these observations are instruments on a Gulfstream airplane in NCAR. Then more information could found in one of the papers in 2015. Elaranta has a very good paper on HSRL. Try to simulate for those instrumentation, we need to have a droplet size versus cross sections. These are all spherical drops. And the mean scattering is good enough. There is no non-sphericity in these particles. Then what we show here is basically a blue curve shows the backscatter. This is Rayleigh scattering, goes up. Then this is basically mean scattering. There's a notch here, about 10 dB notch due to mean scattering here. That's a backscatter as a function of droplet size. Normalized backscatter. Then this one is basically an extinction, the red curve, the extinction measurement. Increases as the particle size increases. These are micron sizes. It's about 1 millimeters here, and goes about factor of 2 as expected here, not in cross section. This is the ratio between extinction to backscatter. It basically decreases, the particle increases, then stabilizes some value. This is for a doubly band 3 millimeter radar observations, what you expect to see each particle size. Same thing with the LiDAR. X-axis, droplet diameter. Y-axis is a backscatter cross-section. But you see the lot of pathological computations. It is not true. By changing a tenth of a micron in a droplet size, cross-section won't change by 2 orders of magnitude. It's a mathematical problem. Reason being, at visible wavelength, dielectric constant of water drop is almost 0 in terms of extinction or no absorption. And there's not much absorption taking place. The photons doesn't get absorbed. And when you do mean scattering, you see this pathological thing. And if you see in literature, very few have done these computations. This is one of the problems with the LiDAR observations. And we can do for small drops, like a tenth of a micron, we can do it. But as with bigger drops, it is not easy to do that computation. This requires a lot of patience, how we do this. We did those computations, finally. It took a lot more efforts to do this. This is a revised LiDAR cross-section. What we see here is the same basically the same size as here, x-axis. Then the blue curve is the same as what we see here. The LiDAR backscatter, this extinction to backscatter. And so once we computed these cross sections, then we could have a model, electron scattering. This is the key. Without that, we can't proceed. We have done a lot of approximations in the literature, d squared LiDAR. That's what they use it. That's not good enough. D squared applies only here, this region here. It doesn't apply here, d squared, the bigger drops. And that is where the problem. And if you have to do a rigorous computation, we need to understand LiDAR backscatter in and out. That's what you have done it. Once we have that, then we need a profiles of droplets in a stratiform, in a stratocumulus cloud. This is an experiment done in VAMOS or in a vocals in Southeastern Pacific in 2008, where we collected our Jon Jensen here. He did a lot of analysis using the droplet spectra from cloud probe, drizzle probes, 93 bins, nicely quality controlled. We got a 4,300 droplet spectra. They're all arranged in ascending or descending patterns. And this is quite important to have the profiles of clouds using in situ observations. This is used as input to detailed electromagnetic scattering model to simulate what LiDAR would see in this cloud, so that we could develop a retrieval technique for estimating liquid water content and droplet size. This is an example of the x-axis 94 events, the profiles of stratocumulus cloud, the altitude on y-axis, the first liquid water content. As the liquid water content increases with the size, this axis here, liquid water content axis here, that's a characteristic size. The size becomes smaller, the blue curve, smaller curve here. It's a typical structure of stratocumulus cloud. And those profiles, what we have it, represents a stratocumulus cloud from the in situ observations. This is the input to a detailed, rigorous electromagnetic scattering model. When you do that, here is the dBz values for the same profiles. The dBz values, as you see here, is a W band at 94 gigahertz. This is the 94 events we have, profiles we have here, the altitude. Then these are values of reflectivity. As reflectivity, basically, as you see, the blue curves about minus 30 dBz values here, much lower. There are values even like you see in the top, the lower values are dBz in the top of the cloud layer. The LiDAR observations here corresponding to that shows much higher backscatter close to the cloud in the cloud layers, but lower values in the cloud below the cloud layers. And this represents the simulated stratocumulus cloud observations of LiDAR observations for 94 events, the 4,300 spectra, what we compute in this one. Now, if you do a scatter plot between the radar and LiDAR simulations, it's almost like random. There is no relation between what LiDAR says, what radar says. We can't do anything with this. This is important to have this kind of independent information. The LiDAR gives you information which is different than the radar information. And you are using two independent measurements, the radar and LiDAR observations or simulation in this case, to retrieve microphysics of stratocumulus cloud. And that is a key. How we do that? This graph shows radar to the x-axis radar to LiDAR backscatter ratio in a dB scale. The y-axis is a size. It's defined like sixth by second movement ratio by 1/4 of that. Now, this is an important concept. We are not defining a median volume diameter. We are not defining a radar effective diameter. Defining something different, a sixth to a second ratio of moments. It's basically dBz. It's a typically equivalent to LiDAR measurement, isn't exact, but that's good enough for this case. The key is we have a DSTs. They're all curve fitted. They're all numerically given numbers. No curve fitting, no log normal, no gamma distributions. When you do that, basically it's a proxy. The radar-LiDAR reflective ratio is same as the size on the y-axis. Hence, there is no assumption about log normal or gamma DSTs. We could estimate the droplet size independent of what type of distribution you see in the cloud. This is the key. Once you do this one, then we could have better way of estimating liquid water content. We may ask a question, okay, the radar estimated size, what I showed with the y-axis here, how that relates to an effective diameter. That's how it is, the lot of scatter. They are related, but they're not good. If you're not estimating effective size, but we're estimating the y-axis droplet size, which is kind of large, much larger compared to the effective diameter for the same spectra. And it's weighted more towards d6th moment. That's why d6th moment here, that's why this is much larger compared to d effective diameter here. If you come to MVDs, MVDs are plotted in the, again, y-axis here. They're much smaller compared to RLES, which is I define as a special character size in this case. This is for cloud and this is spectra. If you do it only for cloud only, if you do that, only cloud only if you do that, then it's a good relation between what I estimated, RLES, using a radar and LiDAR size. This is a D effective. There's a good relation. Narrower the distribution, then there's a relation between what I estimate from cloud radar and LiDAR to that broader distribution, it won't be. But anyway, I come to that point. Again, for the MED, the same thing. We could estimate a proxy for MED using remotely estimated RLES only for cloud, not for cloud and drizzle, because the size is defined such that it estimates only the d6 by d squared. Using those simulations, I've a curve. That means once we know the radar-LiDAR ratio here, they could estimate the particle size. It's a simple relation like this is a dBz from cloud radar. It's a beta backscatter from the LiDAR. That's all you needed. We don't need to assume shape of the distribution. In remote sensing, the two things controls retrievals. One is natural variations or droplet distributions. It could be shape, size, density, all those things. We could get away from that as much as possible, then we can do a much better job. That's why we're trying to do it. And it doesn't care about what droplet distribution or assuming it. RLES could be estimated. Once we know the size, then liquid water content, that's in y-axis. This is the dBz normalized by the size, what we estimated from here. The size normalized with the reflectivity of the HCR or the radar. Then it's a linear relation, what we have. And we can estimate not only liquid water content plus droplet size. And this is algorithm. Now we got to validate how good it is. Here the 94 profiles I showed in the beginning, I have in this Vocal's observations. I picked 4 random profiles here. These are event number 1, 22, and 40 and 41, 80 and 41 like that. Sorry. Oh, I moved it. No, I just have to get it back. Escape. That's not going to help me, I guess. Let's see. Oh, okay. Go to that projection down here. Yeah. Okay. Thanks for that. Appreciate that. Okay, that's the DBC profiles for 4 different events, DBC profiles here. Same with the LiDAR profiles for the same 4 events. These are the simulated profiles from the model, what I showed you earlier. That's a radar-LiDAR ratio, which I needed to estimate the particle size. This is called a LiDAR ratio, they call it. The value is close to about 19 or 20, usually signifies about cloud droplets, but values could be much different. And these are all simulated values, what I did from those 4,000 different droplet spectra, but what I showed you here are 4 different events. Each event may have about 15 to 20 DSDs in this case. Using those as input to the algorithm what I described earlier, that's the estimated droplet size with the height. There are 2 things here, they're one above other almost, and I can estimate droplet size very precisely with a less than 3% error. I can do that. Once I know radar-LiDAR ratio, I can estimate particle size. These are the in situ measurements. The retrieved, they are one above other. You don't see even difference between those 2. And drops could be estimated very, very easily or precisely. This is a liquid water content estimate, the same profiles, the 4 events. You could see liquid water content, but 3 of them are very good. They are less than a 10th of a gram per meter cube, the difference between the error. But one of them is not that good. This has much higher DBZ values, more than 0 DBZ, or the W band in this case is a mis-scattering. And it's not doing a good job. But size could be estimated very good, but I'm using a DBZ values in W band, and that is not in a Rayleigh scattering regime. And there's a big difference in liquid water content between the truth versus in situ measurements, what I retrieved and what I in situ, actually true measurements. And based on this, I got a confidence basically we can do retrieve particle size, liquid water content using a simulations. Now, we need to apply this one to actual observations. Oh, there's one more technique. What we can do is this. I show you just the simulations here. So suppose if you have attenuation, we don't have that in W band currently. We don't have 2 radars. We have only 1 radar. And if you have attenuation, the liquid water content could be estimated very good. And if you use the same methodology, they can estimate liquid water content for all the cases. Instead of worrying about DBZ value, I can estimate even for higher dB, I can estimate it. And these are possible, but currently we don't have that attenuation measurement in the G5. All we have is just a W band. We don't have a Ka band or other frequency. And this is possible in future if you have a second wavelength. But at this point, we have to rely on radar and LiDAR observations. Okay, the next few slides we talk about validating the retrieval technique. All I showed you was simulations. Then I picked 4 different profiles, showed yes, things does work, but really does it help in a real-time measurements or even real measurement in the field measurements. For that, we use the CSET, Cloud System Evolution in the Traits. Northeastern Pacific, 2015, we got this measurement. Recall, DSDs, droplet size distribution, what I used is from Southeast Pacific, from Stratocumulus cloud, not from this experiment. The Stratocumulus clouds from Southeast Pacific were used to simulate those profiles or Then I used a CSAT, Northeastern Pacific observation to validate this. And there are two different geographic regions. Still, the physics is right, it has to work. Now, remote instruments, what we had in the CSAT is a cloud radar. Then we have HSRL. It's all the things we did as simulations in this case. Then we have a radiometer. Because we had only one airplane flying into the cloud, and so you don't have two airplanes to validate our observations. We have only one aircraft, you have to look at it. The radiometers are helpful in that way. I'll show you why. But the different footprints, this is important. Like a radar has a 435 meter, depending upon how far away the cloud from the radar is, because the beam is diverging. HSRL has only 40 centimeter footprint. It's much smaller compared to, talk about meters here, tens of meters. Radiometer, about 50 meters or so. So all these instruments have a different footprint, looking at the Stratocumulus cloud. Still, could we do the retrieval and come up with a reasonable values of this? Footprints about 70 meters, because averaging about 0.5 seconds, the aircraft flies about 140 meters per second. 70 meter footprint size as every half a second if you do that. One more problem, the HSRL LiDAR is not pointing down. It's pointing 4 degrees away from the fuselage due to away the glint from the sea surface. And that creates a HCR footprint about 140 meters at 2 kilometers. We're talking about many instruments, but they're not, even though they're co-located in the time, spatially, the different spatial resolution, and also they have a different, looking at different place also. With all these things, still, we should be able to show at least does things does work or not. Briefly, I'll show you the cloud radar. That's the lens antenna, the reflector. It's all pod-based system, 20-inch cylinder here, where we have this radar housed here. So these are very good measurements. It's mounted on a right wing of the airplane. That's in a pod. Of course, G5 can a lot more in situ probes also. But when you have remote measurements, we don't have in situ measurement. We have only one airplane, and that's the problem here. We have to be careful how we do these measurements. So then the cloud radar specification is about, it transmits 1.6 kilowatt with a 0.7 degree beam width, and it has a very good sensitive DBC measurements could be done with this. Look at it, it has 1.6 kilowatt power. It's a lot of power with this W-band system, the Klystron. So we have that. The LiDAR is in a cabin-based system. It's within the G5. It's in a visible wavelength, in a green light, as you say it. Then 4 kilohertz. It's an eye safety, because micropulse LiDAR, we can do that. And the field of view is about much smaller. The 40 centimeter is a footprint for LiDAR. And these instruments are well-calibrated, well-maintained instruments, and it gives a very good quality observations. The LiDAR block diagram, if you look at it, it's a blue basically shows the transmitter blocks. The red is receiver channels. The key thing here is the beam starts with basically a 1 millimeter beam here, expanded into a 20 millimeter beam, then goes out the 40 centimeter beam. That's the LiDAR does. And then LiDAR has 3 channels. This is important. It has a combined signal, which basically means from atmosphere, you're scattering from molecular scattering and aerosol. Both get measured. Then we have an iodine filter, iodine cell. That kind of filters out molecular channel. Basically, it does molecular only. It basically does that by filtering. Then we have cross-pole measurement. Since you have combined signal, which aerosol and molecular, and only molecular channel could be measured, then a cross-pole signals. Why it's important? When you have a molecular channel, we could correct for attenuation of the LiDAR measurements. This is important because what we measure in HSRL, the backscattered, corrected for attenuation. That's an important quantity. If attenuated LiDAR is not that useful to us, and this is important measurement. And so LiDAR gives the attenuation corrected backscatter measurements. It has the 3 channels. And these are all one of the best instrument what we have on a G5. This is basically a technical spec for the LiDAR. It pulses 4,000 hertz. Compared to 1.6 kilowatt, what I showed you for a cloud radar, it does transmit about 300 milliwatts. But still, it's sensitive enough to pick up aerosol and cloud droplets, what I'm going to show. So next few slides, I'm going to show you how these instruments, data, what we measure in the instruments, are used for retrieving cloud droplet size, liquid water content. This is from a CSAT measurement. Remember, I mentioned that all the simulations are done using a South Pacific measurement, in situ measurements. But application is done on North Pacific observations. Still, it does work. I can show you. This altitude, that the 5 minutes of G5, altitude 100 meters, if flying very close to the ocean, looking top, that's the DBZ, what we see here. About minus 10 or minus 30 to minus 5 to plus 20 dBz. This about flies 140 meters per second. This about 42 kilometers in distance, looking top like that. Basically, it's basically looking at zenith mode, looking up. Same time, these are LiDAR measurements. That's in a beta. This is a DBZ, that's a beta. The LiDAR observations are basically show the cloud very nicely here. That's the drizzle, you can show here. And again, this is a drizzle streak. That's corrected for attenuation. You can see a slight difference between the DBZ corrected for attenuation. LiDAR is already corrected for attenuation. That's important to do that. But radar is corrected for attenuation using a power law relation. And these are the observations. Radar observations with the height, with the time. It's about 42 kilometers. Algorithm what I described using radar and LiDAR observations. The top panel shows droplet size. That's a log scale. You can see the droplet so small. They're about 10 or 12, 15 micron droplet size. These are droplet sizes here. Second panel shows the same plot, liquid water content, about 1/10 of a gram, 2/10 of a gram per meter cube here. And you see the drizzle, lot of dBz, very low, 100th of a gram per meter cube liquid. So all the liquid concentrated on cloud droplets here. And this fits very well, the structure of a stratocumulus cloud. And how do you know it's right? I mean, logically it fits right. If you go back. This is the same time, remember I said of a G-band radiometer. Radiometer came from Pro Sensing, operated by University of Miami, Paquita. This radiometer, the same time, the 1920, the blue one from what we estimated from radar and LiDAR, totally integrated over the path, the blue one. The red one radiometer. Yes, I was so surprised to look at this kind of comparison or even agreement between those two measurements. One is a passive measurement, totally independent of radar and LiDAR. The active measurement is the right, radar, LiDAR. The passive measurement from microradiometer of 183 gigahertz. It computes, basically estimates total path of liquid water path. And shows a very, very good agreement. Given I showed you the footprints are much different. Radar has hundreds of meters. LiDAR is 40 centimeters. The actors moving at 140 meters per second. With all those conditions, are still able to replicate in a qualitative sense the radar, LiDAR observational liquid water path. This is 5 minutes, about 42 kilometers in distance as we did the observations. This is that's July 24th, what I plotted showed here. This is one other case. This is a 10 minutes path. 5 to 15, but 84 kilometer. Again, Stratocumulus cloud. Radar observations, the height. The LiDAR observations shows multiple layers of cloud liquid in this case. Then attenuation corrected DBZ values, you can see the difference. Corrected was much higher than uncorrected values. And this second case, 84 kilometer. Again, aircraft is looking up. That's the aircraft altitude, about 100 meters above the sea surface. Looking up, got the measurement. We retrieved using algorithm what I showed you earlier. That's the liquid water. This is a droplet size. They're much smaller. They're log scale, but 10 to 12 micron here. Showed all the places. Come up with again liquid water content log scale here, larger where there are small droplets percent like that. So again, this fits closely with what the Stratocumulus cloud is supposed to have. Small drops, a large liquid water content. It's much different than a rain rate, where you have a larger DBZ, larger rain rate, but it's much different when you look at it. And something I learned quite a bit looking at radar and LiDAR observations in the Stratocumulus cloud. This area is very rich in terms of investigation research. Then how do you compare? When you compare the same thing what I did earlier, the radiometer, that's a red line. The radar, the blue line. There's a good agreement here, not a great agreement here. I'm not surprised in this, given we have a footprint differences that much. But still, there are like peaks kind of aligns with that. There are peaks like that. Other things here. So overall, the agreement, I showed you two cases. One is a 40 kilometer in space, lengthwise, 82 kilometer. Both the cases, 2 different days, shows a reasonably good agreement between what we estimated from the blue curve, radar and LiDAR, the red is radiometer, the passive measurement, active measurement, 2 different techniques. Okay, the next question is, how good are these retrievals? Assuming standard deviation radar reflectivity about 10%, about a 1 dB or so, LiDAR again about 10% in backscatter measurement, the expected standard error in droplet size is about less than 4%. That's why I'm able to show you droplet size is very precisely without much of error. You can estimate the droplet size. Almost the in situ and the retrieved measurements are almost same. Liquid water content about 10%. That's the error we're talking about. Hence, we're estimating remotely droplet size, liquid water content with great accuracy. For a rain rate, if you compare it, about 35%, even with a Z and ZDR and FDP even today. But this is a much better retrieval if you can do it, less than 10%. But these are important to do this because we're talking about small drops, not a liquid water content, highly, they are varying in space and time. And this is my last slide here. In summary, I showed you basically a simulations from vocals. Same could be done for Caesar and Socrates, the other 2 other deployment where you have cloud droplet observations. We can do the simulation if you wanted. Retrieval technique is doesn't assume a shape of the droplet spectrum. It's all spherical shape, of course, but it doesn't assume log normal or gamma distributions. They're valid over large dynamic range, about 30 dB dynamic range. Compared to currently what we have is less than 15 or 20 dB at the most. Even then, we need to have a lot of a priori information to do that. We need to know whether it is drizzle or cloud droplets like that. And this is a key, independent of shape of the droplet spectra. And retrieved quantities are agree with radiometer observations. So this technique, basically what I presented today, Once it validates a bit more, it will be implemented in a G5 instruments at some point, just for estimating cloud droplet size, liquid water content. It's the first scientific product which we implemented using 2 observations. Even though we have different footprints, it's looking at 2 different directions, with all those things, still there are values in getting those kind of observations and come up with a much better way of describing microphysics in a Stratocumulus cloud. I would stop here and ask any questions.
Thank you very much for this very interesting seminar talk. Are there any questions?
So a lot of it showed a very nice match, but your last radiometer to radar LiDAR wasn't nearly as good. And I don't know if the problem is in the radiometer, if the problem is in the retrieval, if some of the clouds are more spatially inhomogeneous and these sorts of things. So have you got an idea for why it was not better than what you showed?
Yeah. Based on simulations, I would concur. Simulation very good. There's nothing wrong with that. I think spatial distributions, footprint differences. You're talking about 40 centimeter LiDAR looking at least 100 meters away from the radar. How much inhomogeneity you can have it. Even then, we're able to do that. That's very surprising to me. This could be validated a bit more, having more homogeneous cloud, because these clouds may be maybe the first cloud what I showed you, a bit more homogeneous. I got a much better comparison. The second case may be a lot more inhomogeneity, and also it has multiple layers of liquid layers also. We don't know how it was, and vertically we have seen that. Maybe it is horizontally it's different too, because looking at 2 different directions here. I would say at this point, it's more related to spatial inhomogeneity. But we can't really say how much spatial imagine, because we are looking only the one B scan profile, and we don't know how the adjacent things look like that. And that's a limitation with the observation what we have, unless we have some other observations. So that spatial imagine, we don't have those kind of validation, how homogeneous the clouds are. And that's something which I'll look into it.
Hey, Vivek. The Wyoming King Air flies cloud radar and a LiDAR as well. Can this technique be applied to their data sets?
Yes, it should apply, provided their LiDAR is not same as our LiDAR.
I know it's not exactly the same. That was my question.
That's right. Because LiDAR world, the key is, remember I showed you the cross sections. In fact, that's see, this is where the problem is. People assume that D squared. It's not D squared. And most of the D squared assume it. They don't correct for LiDAR attenuation with the cloud. This thing makes a huge difference in the retrieval technique. And yes, it will apply. Nowadays, many HSRLs are coming in place. These high spectral LiDARs are coming more common. And these LiDARs are much better quality in terms of thing. And we have those kind of observations. Yes, it should work. In a sense, it should work. The Wyoming radar, what we say, LiDAR, that's right, it should work.
Should work. We have some orographic data sets that have very clean liquid water profiles. You might want to take a look at.
This is from experiment you did in Oregon?
From Snowy, yeah.
Snowy, okay, good. Yeah, we could try that.
Any other questions?
Thanks for sharing, Vivek. Very interesting work. So I may have missed something, but on I think it was the CSET case. So like if you look at the LiDAR data, the vertical profile you showed, it looks like there's an awful lot of attenuation in the signal, which you would expect for a LiDAR. But then when you do the integrated, I think you were plotting the liquid water path integrated through the cloud. I was surprised it was so good when there was so much attenuation in the LiDAR signal. Do you?
Yeah, the LiDAR signals get attenuated. Actually, this is, I didn't tell you one secret here. All the observations are done vertical pointing. Hence, we are able to see both drizzle drops and cloud droplets. Suppose I did other way around from the cloud top. What you're saying is correct. LiDAR won't see past the liquid cloud. All the cloud will extinguish LiDAR signals. And so that's one problem we have at this point. And data what I showed you, there's attenuation only above the cloud region, which is not a matter for in this case. That's why I able to get good comparison. If I did other way around, looking from the top to bottom, like a zenith, basically a nadir pointing, then I will have a problem with this kind of technique. And this is good for ground-based radars or ground-based technique or flying close to looking at the zenith mode. That's where things really work. And so we need both LiDAR, radar observations to do this. We can't do one. I showed you why. If you are just only DBZ alone, you could come up with X number of power law relations only tuned to that kind of situation. Is not going to work for a next time period or next time even pixel. And this technique is supposed to work independent of spatial and the differences in radar and LiDAR measurements. And that's how this is using. It's like a dual wavelength technique, except LiDAR getting used. The first time, I talked to some of the DOE people sending some manuscript. They said, well, we have been working on this more than 40 years. They felt this technique seemed something different than what they have looked at it so far. I was so surprised to hear from them, DOE people. So I'm kind of newcomer to this. I didn't work on about 3 or 4 years on this after getting into this LiDAR radar observations.
Any other questions? Last chance? There's one more.
So this is regarding to LiDAR. I have two questions.
Pardon? Go ahead.
What is the need to expand the beam? And second one is how to correct that solar noise from the backscatter signal.
Okay. The LiDAR, the beam is not expanded. The power is highly concentrated in a very small beam, a lot of power. It's not eye safe. To make it eye safe, beam is expanded. So that it could be flown on an airplane or deployed in a city. That's the LiDAR. That's micropulse LiDAR. The only disadvantage of this one is because LiDAR is such a low power LiDAR, because expanded beam, it needs a lot of photons to make the measurements. It takes half a second integration to get a good measurement. That's the problem. If you have very high power LiDAR, we can sweep the LiDAR and get observation just like that, like a radar. It cannot be done. It takes half a second to get a measurement like that. That's the problem. In half a second, aircraft flies about 70 meters, and we got the average profile. Another question we had was? Solar noise. Okay, this LiDAR, it's not affected by solar power because it is the power from the LiDAR. It's much stronger. It's not like a Raman LiDAR with the background noise that's going to propagate. And so we have excellent LiDAR engineers here who did a very good calibration of this thing. And so we trust the quality data is very good. It basically what it transmits at visible light. It measures the observation of visible light, optical depth in visible light. This is quite important because all the short wave long radiation all based on the solar spectrum. This is quite helpful to do that. I didn't even dwell on extinction measurement. What I showed you was just a tip of a LiDAR data set, backscatter. And there's a wealth of information exists in extinction measurement, which you haven't even touched on that yet. Yes.
So just as you're talking there, why couldn't you also expand the LiDAR beam to make it broader and therefore get the same footprint, or is that just a stupid question and impossible?
Maybe Matt Heyman could answer that.
Why would you need longer time? You have the same power going out. You still integrate over half a second.
I mean, there's pretty practical that requires that we expand the field of view. And when you expand the field of view, then you need either to open up your narrowband filtering or you need a really large narrowband filter. So it's not really practical. All of a sudden you're worried about solar background overwhelming your receiver. So you need a very well collimated beam.
The next, the EarthCare satellite, I guess they have the HSRL on board. Like Calypso had only the simple LiDAR. Next one's the HSRL actually, what's put on the orbit. And we are talking about LiDARs which are highly practical in what they have it in the space. And this technique, what described to you, and it should apply to some of those space-based observations too. CloudSat and EarthCare observation kind of that. Thanks,
Okay.
Matt.
If there's no other question, then let's thank Vivek one last time. Thank you, Vivek.
Thank you.